Okay, so in this lecture, I'm going to talk about the difference between internal and external forces. And what I'd like to do is generalize our idea of the momentum principle to take into account multiple particles or multiple objects within our system and our surroundings. But what I want to show you is that in doing so, we get back to a very simple evaluation of all of the internal forces versus the external forces. Okay, and so as you can see, I'm going to eventually end up taking our complicated thing and I'm going to turn it back into our spherical cow. For all intents and purposes, we have a system that we can generalize and then simplify. Okay. So as we know, the momentum principle tells us that the change in momentum for a system is equal to all of the net forces, the sum of the forces, in some time interval delta t. This is our favorite equation. And I can say that P or delta P for my system, so if I think about my momentum for my system, not necessarily the change in momentum, just the momentum of a system, here's my system, of a group of particles, it's going to be P1 plus P2 plus P3, and I could go on and on and on and on and on until I have an infinite number of particles. Here I have 3, but I could have many. And also, and this is the beauty of all things vector, is that we can just sum the vector forces and the vector momentum. So the net forces, of course, are going to be F1 net plus F2. Call this net. I'm going to say F2 plus F3 plus dot dot dot. So again, all I'm stating here, nothing new, is that things like momentum or even changes in momentum, whether these are initial or finals, it doesn't really matter. We can always take all vector quantities that we're calculating and sum them to get what we might have for the system, and we can sum to have the net forces because they are also vector quantities. So vectors make our life slightly easier. Okay, so now let's think about our system of particles that we have identified. And so let's look at what we have. And we do this in our calculations all the time. If we take the Earth and the Sun, and we call one the system, let's say the Earth the system, and the Sun as the surroundings, then in the Earth, imagine all the particles, all of the atoms that make up the Earth, and you and me and the buildings and the oceans, and we've lumped that all into one spherical Earth that incorporates every particle, every object, every massive body, every butterfly. That's all George and Martha. They're all encompassed in our system. So we're doing this right now. When we do calculations, we don't care about every helium and every, carbon nucleus and everything in the sun. We just call it the sun and say it has a mass. So we're doing all of this already. And so what we are saying by assuming this spherical cow is that all of the internal stuff that's happening between me and the Earth, between a car and the road and the Earth and the cloud and whatever, all of that stuff, all of those internal interactions, the ones I've got here in lowercase, all those internal interactions and internal forces, they in a sense don't matter. What we need to think about is the system itself. But we still need to be able to prove that that's the case. So let's do that mathematically. Okay. So I have three particles, M1, M2, and M3. They're interacting with each other with equal and opposite reciprocal forces. So F on 1 by 2 is the identity in magnitude, opposite in direction of the force on 2 by 1. And similarly, the mass 2 acts on mass 3 with a force 2, 3. That's reciprocal to F force on 3, 2. So that's this force and this force. They are a pair, a reciprocal pair. And identically the same relationship between M1 and M3, where I have F13 is the equal and opposite pair force with F31. And so these are all reciprocal forces. Okay. Now, in addition to that, I have drawn this dotted line, and I call this my system. Internal forces, these lowercase forces, are my internal system forces, and they all add together to give me my system. What I've also done is I've said that somehow there's a set of objects that I'm defining as my surroundings, which are outside of that dashed line, that exert individual forces on all of these masses, and those will then sum to give me the net force from my surroundings acting on my system. And so what we're going to do is we're going to go through the momentum principle for this multi-particle system and analyze all of the forces and all of the changes in momenta for each of these particles. So what I'd like you to do is perhaps copy down this, put this on pause for a moment, copy this down so you have a reference, and then what I'm going to do is I'm going to go ahead and erase this and we'll continue. So pause the video, copy down this schematic, leave the cow, and we'll go on. Okay, so now let's go through and analyze our particles one by one. This is going to be a bit of text, and it's going to take a little while. So here we go. Let's think about the change in momentum for particle 1. That's going to be equal to F due to on 1 due to the surroundings. So I'm going to sum up all the forces plus F on 1 due to 2 plus F on 2, F on 1 due to 3 times delta T. It's just the momentum principle for that first particle. So this is particle number 1. Particle number 2 is going to have a similar look. Delta P2, sorry, that's momentum. F on 2 due to the surroundings plus F, well, now I'm going to put 2, 1 plus F 2, 3 delta T. This is particle 2, and of course particle 3 delta P3 equals F on 3 due to the surroundings plus F 3, 1 plus F 3, 2 delta T. That's what's on particle 3. Okay, now I'm going to sort of work as a big column sum here. P1 plus P2 plus P3, delta P1 plus delta P2 plus delta P3. Make sure I have all my vectors on. Okay, so everybody's a vector except for delta. Okay, so now let's add all these up. 1, 2, 3. That gives me delta P1 plus delta P2. Woohoo! That's delta P3 equals, bring down my equal sign. Well, we're going to have to sum all of these things up. So, I'm going to take all of my surroundings and sum them up. F1 due to the surroundings plus F, everybody's a vector, F2 due to the surroundings plus F3 due to the surroundings. All right, so the force on 1 due to the surroundings, force on 2, force on 3, that's these. And now I get all of my reciprocal pairs. So, let's look and see what we got. We've got F12. We've got F13 plus F21 plus F23 plus F31 plus F32. That's a lot of forces. But we know that those forces were reciprocal pairs. And every time I switch the index, I pick up a negative sign. So, F12 is actually the negative of F21, and vice versa. These two equal 0. F13 and F31, I link those, they're also equal to 0. F23 and F32, I link those, they're also equal to 0. So what I can say, oh, I forgot my delta T. What I can say is that all of the internal forces are gone because of reciprocal pairs. And we could say it's gravity that's acting internally, so we could call them Newton pairs, whatever we like. So what are we left with? What we're left with is that delta P1 plus delta P2 plus delta P3 is equal to F1 surroundings plus F2 surroundings plus F3 surroundings delta T. And if we look very closely at this, these are the change in momenta for my system. As drawn, these were the momentum changes of my particles within my system. This is delta P of the system. It's the total change in momentum of all of the things within my system. And this is the sum of the net forces from the surroundings. And I'm going to put surroundings up here, just to remind us, times delta T. Which is amazing. We went from all the internal stuff that was going on to not having to worry about it at all. All of our internal things, which we've already been doing, we've been sort of sweeping this under the rug, those all go to 0. All we have to worry about on our system are the sum of the net forces external to the system, working on the system from outside, and all of the change in momenta of the things within the system. And that's a really powerful tool.